In this exercise, we have a few fractional equations with parameters, but we only are asked to solve them naively, so not discussing special cases, extraneous solutions, all of that. So we just try to isolate the unknown on the left-hand side, and the solution will then be a single expression on the right-hand side. So let's see, for number A, let's get rid of the fraction by multiplying with 1 minus x. So we get 1 plus x equals a times 1 minus x, which is a simple linear equation. So this fractional equation is actually just a linear equation in disguise, except for the value x equals 1, which would be an extraneous solution. So we solve our linear equation. So we get x plus ax is a plus 1x. And here we get a minus 1, so x equals a minus 1 over a plus 1. We don't write this as a solution set because we're not discussing any other form of a solution set other than a single solution, single value in it anyway. So for part number B, we see that we have two fractions and we will just apply the cross rule. That would be the simplest one. And now let's expand. 3t squared plus pt minus 3pt minus p squared equals, and we already see that the squared term vanishes. We are left here with minus 2pt minus p squared, and here it's 2t minus 1. We remember that t is the unknown, so we collect linear terms in the unknown on the left-hand side and the constant terms on the right-hand side. So minus 2t plus p squared gives us minus 2 p plus 1t, so I already factored, and p squared minus 1, so we can now divide out this factor, and notice that p plus 1 is a factor inside p squared plus 1. So we are left with t equals minus p minus 1, 2. The factor p plus 1 cancels out, so we can write this simply as 1 minus p over 2. Now the third equation, looks complicated, and then we first look at the denominators and recognize the third binomial formula on the left-hand side, on the right-hand side. So the common denominator is just y minus r times y plus r. So we multiply with this common denominator right away. So the y minus r cancels out this factor, and we get another factor y plus r, so squared. And the second fraction, the factor y minus r, y plus r cancels this one, and we get an additional factor y minus r on the top. And here we get well, we just cancel out the denominator. 4r squared plus 2r. And we expand. And we get rid of the bracket here. This is plus, this is minus. And we recognize that y squared cancels here. R squared cancels here. So we are left with 4 ry equals 4r squared plus 2r. And we would like to divide out r. Why not? We're not paying attention to special cases, extraneous solutions, all of that. But, well, we can already say if r were 0, then we would have any real number as a solution, well, except looking at the denominators, r and minus r, which is just the single number 0. But I'm not asking this from you. So we get 4y equals 4r plus 2. We divide out 4 and get y equals r plus 1/2. Finally, the last fractional equation contains lots of double fractions. Now we can get rid of the double fractions by either multiplying with an appropriate factor. I mean expanding the fractions with appropriate factors x times c times d, or we can put the numerators and denominators separately as single fractions and then rewrite the double fraction as a product of two fractions, taking the inverse of the denominator. So I prefer the first method, but maybe just to reactivate what we've learned in the winter, let's use the second method. So 1 over x plus 1 over c, we need to make it under the common denominator. So we need a c in the first fraction and an x in the second fraction. And for the denominator, it is the same pattern, just with d instead of x. So the whole fraction on the left-hand side becomes c plus x over cx, now divided by d plus x over dx, which is multiplying with the inverse. And the same thing on the right-hand side, actually in a simpler form. 1 over d over 1 over c is 1 over d times the inverse of 1 over c, so it's just c over d. So we get the equation c plus x times d over c times d plus x, where I have already reduced with x. And this becomes c over d, so we still have to do a little bit of work. So a cross rule that gives us d squared times c plus x equals c squared times d plus x. Notice that the symmetry between c and d is still in this equation. If the symmetry had disappeared by now, if d and c would no longer play the same role, that would be a big indication that we had made a mistake. The original equation treated C and D in a very symmetric fashion. Well, not quite, but there's a nice pattern. And if the pattern had been broken here, so if this had been C cubed or just C, or we would have had a minus sign here, that would have been an indication that we made a calculation mistake. So the equation is linear in x, so that's what we're looking for. So we need to put the term x on the left-hand side and the constant term b squared c on the right-hand side. So we get d squared minus c squared times x equals c squared d minus d squared c, and we can factor and it looks as if we can divide out c minus d, except that this gives us a minus sign here. Well, actually, let's put the minus sign on the right-hand side. So we are left with d plus c times x equals just minus cd. So x equals minus cd times c plus d.